Okay, then welcome to the exercise to lecture 6 in parallel and distributed computing. We have a little bit of introduction. So today the exercise will only cover the master-slave process, and will take this at an example of calculating pi. Yeah. So there are much more efficient ways of calculating pi than what we're talking about here. But you know, the focus is on doing something that requires parallel computation. So actually, we have some incentive not to do it most efficiently. There can be two approaches, but I think we'll cover only the other one we do next time. Yeah. So there's a master and slave approach, and then there's divide and conquer. But for divide and conquer, I need a little bit more explanation. So pi is a relation. So pi is often seen as the relation between the circumference and the radius of a circle, but you can also see it as the relationship between the length of the curve and the volume that is covered. So you can actually put it as an integral. Yeah. So or you could say, okay, put it the other way around. Yeah. So a unit circle has an area of pi. Yeah. So then if we take only a quarter of this circle, then we'll have pi divided by 4. And this quarter of a circle we can actually describe with this circle function that we have up here. So this is square root of the radius squared minus x squared. Yeah. So this is this curve for the circle in this one quadrant, meaning that if we integrate this square root 1 square, so square root 1 minus x squared from 0 to 1, then this integral is supposed to be pi divided by 4. So this is a way to compute pi, by multiplying this with 4. So this means we can use very simple integration technique. So the most simple integration technique is simply saying that we sample these points. We do what is it? Equidistant sampling of the points, and we divide by the number of points, and we multiply this by the length, and the length is 1. Yeah, so we multiply by 1. So this is the most primitive way of one of the most primitive ways of computing pi, or pi quarter. Okay, so now this is supposed to be done now as an exercise in an exercise for MPI. So I've put the file in PVR 2025 Gaia lecture. So it's lowercase Gaia. Okay, lowercase Gaia lecture 6, and then there's main serial. Now you are supposed to take that file and copy it to your folder. We'll look into this in a minute. Or we can actually do this now. Let me see. So, okay, I have a non-working mouse here. So let me see whether I'm in the right. Yes. So I have. So we have this PVR 2025. There I have my folder Gaia. There's lecture 6, and then there are 2 files here. I mean, there are a few more because I tested this yesterday. But there is this main serial.cpp, and then there's also a job file, yeah, because we are supposed to do this on why is everybody blinking so dark suddenly? Yeah, so there's also a job file. Okay, I've taken this file from some colleague who prepared this. So let's see whether we actually understand this. So in order to see what mistake we make, we first define pi, that we have something to compare to. Yeah? And then sorry. Sorry. Then because we do not want to write a header file for this, I include, so to speak, my header in. I declare my functions here. Yeah. So what I could do is I could define my functions here. Then it would be clear. But in C, you always have to declare functions before you can use it. This is basically also the reason why you need header, because otherwise it does not know where that the function exists. Yeah. So when you don't want to use a header and you want to have a simple program that only is one file, then you need to declare the function first, and then you can, implement it later. So this is why we have here these declarations. So what we are actually going to use is here this main function, and then there's already a few things implemented here that are not obviously not necessary for serial code. Yeah, namely, number of processes is now set to 1, and my rank is set to 0. Yeah. Then there is something that's a little bit useless, but I left this in. There's a number of repetitions, because this program is usually so fast. If you want to measure the time, then you run it several times that you can actually get a realistic measure of how long it would take. Okay, so we initialize our result with 0, and then we do domain decomposition. This means we have a local integral, yeah, that we would evaluate. And then there's also time measurement. So we start the time measurement here, and here we set some number of intervals. You see they are pretty large, so it's a pretty large number of intervals. And we have an upper limit of we have a lower limit of integration. This is global A, and we have an upper limit of integration that is local B. Yeah, so it's from 0 to 1. So here are repetitions. Then we do our local number of intervals. Number of intervals divided by the number of processes. That would be 1, obviously, in this case. Then we have local interval width. So this is how big our interval is. This is global B minus global A divided by the number of processes. Again, local A. So this is the part, the slice of the integral that we would compute. So you see all of this is already prepared for you, yeah, so that you only need to deal with the MPI part. So then what we do is we calculate the local integral, then we add the local integral to our result. In between here we would have to do the communication. Then here, because we repeated this, what we do is we take result is result divided by the repetitions, which, yeah, if we do several repetitions, yeah, would happen, and then we do an output. And the output is only done if my rank is 0. Yeah, so there's already a kind of a master process, and then we return 0, and in between here we have this, after this, we have this integral of this integral function that gets the upper and the lower limit, and how many parts you would divide this in. Then we simply do the integral of f, and in f is the function that we integrate. Okay. Any questions regarding this program? No. So then the way we are going to run this. So there's one thing I guess we have to look into. So there, I mean, I told you last time that again we will talk about the job file. So this job file may not make a lot of sense now for the serial process, yeah. So what we have here is the number of nodes that we want to run our code on. That now I've set to 4, and the number of tasks per node, which I also set to 4. So in principle, these nodes, they have two processors with 10 cores each. So if you want to maximally use one, then you would here write 20. Let me now do it like this, that I say we take 2 nodes, but we only use half of them. Okay, doesn't make a lot of sense, but just for the illustration, yeah. Then, okay, so it has a working directory. So, and then what is important here is that there is this, that we run the code. Now it's a serial code, so the serial code you would usually run without MPI. Yeah, so you could run this like this. Let me save this and let me go to CD PV25 and then to Gaia. No, yes, Gaia. And then we will go to lecture 6. So this is, but you remember this is my folder. So you can copy the main serial, and you can also copy the job file, but don't compile anything here. Yeah. So let me compile it here. So I use MPI CPP already because later I want to do this using MPI, so and this can also, of course, be used without MPI. And I want to compile this minus, so pi, I've already done this, so I didn't change it, it should run. And the thing with the job file now, yeah? So, since there is no MPI in this, I simply use the executable. Yeah, I can use the executable. I can run it. I can run the executable on the login node, which I'm not supposed to do, yeah, but which I'm now doing because it's it only takes 4 seconds. What we are supposed to do is we are supposed to submit our code with this job file, and we do this by s-batch job file. So now I submitted it, and it got the handle 88688. So what I'm expecting, that it again will take some 4 seconds or so, as long as it's not standing in the queue for long. It may stand in the queue for some time. I hope that no, I needed. Okay, we can. Okay, now I needed Konstantin to tell me how I look up the state of this oh my God. How do I look up?
Should be finished already, right? Because it was not done.
Yeah, it should be done now. No, there is something. I wonder whether okay, let me use it with MPI run. S-batch job file again. Now we get a new one. Okay, yesterday it worked. Maybe you are standing in the line, I don't know. Okay, I don't know whether this task per node was a problem. Let's do this again. Okay, I don't know whether they are standing in the line. Let's briefly go back to what we are supposed to do. Okay, now yes, understand and run it, and then introduce the MPI stuff. And so there are different ways how you can implement this. And today we'll, I guess, only cover the first one, which is using a master-slave approach. Then there will also be divide and conquer and group communication. But let's look at this master-slave thing, which has, of course, a bottleneck. So say what we are going to do is we cut our problem in pieces. Yeah. So these are our slaves. Each of them calculates one part of everything, and then the master collects all their parts and adds them together. Yeah. So you see, depending this will usually work very well. The only problem is if you have many slaves. If one master has many slaves, and there's not too much work to do, actually the master, because the master has to talk to each of the slaves, so the amount of work that the master has becomes the larger the more slaves there are, right? Which is a little bit, counterproductive in speeding up parallel work, right? But this is so the assumption is that the slave does much harder work than the master does, such that it's still fast. Yeah? But, there's, of course, these problems coming up here. Okay, so this is now what you're supposed to do, and what I'm doing, I'm stopping the recording, and I will look up whether what may be the problem here.